So I said that the hardest part of calculus is algebra. The other hardest part is probably notation and just getting a real sense of going from, okay, just solving equations to really understanding how to communicate in the math language. And so we're going to do just a very brief introduction to set notation because we're going to move into talking about functions defined on sets. And so the first thing we have is the natural numbers. You'll see this little blackboard N is the symbol. So that's just the counting numbers, 1, 2, 3, 4, etc. You have the integers, that's denoted by the blackboard Z. And we include 0 and all of the negative numbers. Then we have the rational numbers, denoted with blackboard Q. And these are basically fractions, but they're just quotients of integers, where of course the denominator cannot be 0. We can't divide by 0. And then what we're really interested in is the real numbers. That's what calculus is really going to focus on. It's going to focus on the study of functions defined on the real numbers. And so what are the real numbers? Well, it's pretty easy to follow how to define the rational numbers if you believe there are these things called the counting numbers that allow us to enumerate sets, and then the integers, you just sort of generalize, you add in 0, which was a big deal. You added negative numbers, which was also a big deal. And then you just take quotients of those to get the rational numbers. But what are the real numbers? Well, the real numbers are just the rational numbers with all of the holes filled in. And I'm not going to spend a lot of time saying much about that. If you take a class in advanced calculus, or analysis is what it's called, then you'll talk a lot more about how the real numbers are basically defined from the rational numbers. And so I guess the only thing I'll say is, what do I mean here by whole? Well, it turns out that there are holes in the rational numbers. So in other words, if I think about, well, is there a real number x such that when I square it, so I multiply it by itself, I get 2. Well, it turns out that x is not rational. So if I define this thing called, let's just say the positive square root of 2, the number that when I square it I get 2, this x is not going to be a rational number, which is kind of a deep problem. Somehow you might think that all numbers are rational, but it turns out that there are numbers that are not rational. And so those are kind of the holes that exist within the rational numbers, and that's really all I want to say about that. But what I do want to connect up is, once we have this idea of the real numbers, calculus is pretty easy to nail down. So calculus is the study of functions defined on the real line, or more specifically on subsets of the real line. And what we'll do next is we'll actually be a little bit more specific about what types of subsets we're going to focus in on. So when we get into different types of functions, we're going to start throwing out domains of those functions. And we're going to get a lot of things that look like this. Closed intervals, open intervals. This is kind of halfway a joke. Clopen intervals, so closed and open intervals. Closed rays, open rays, and then we can combine intervals with these operations, unions and intersections. And I'll just leave this here as a reference. You can look it over and try to make the connections with everything. I hope that you've seen this before, but we just want to review the main idea. So notice, first of all, notationally, that when we use a square bracket, we're including that endpoint. When we use a parentheses, we're not including that endpoint. On the right-hand side here, I'm using this set builder notation. So we'll see this time and time again. And especially if you go into any more advanced math classes, it comes up a lot more. But the idea here is that if I write, okay, so I'm saying I want a real number x, so an x that's in the real numbers, such that some property of x is true. So you see here, the property is that x lies between these two numbers a and b. But in general, it's just saying I want a real number such that some property of that real number is true. And then that defines a set. Now the set might be empty. There may be no numbers x that satisfy this property, but that's the idea behind set builder notation, and we'll see it here as so. So the last thing I'll mention is that actually we can write the entire real line in interval notation as just minus infinity to infinity. And there's also these cool diagrams you can draw. So for instance, if I have this interval here, then I can plot this on the number line like so. So here would be 0, and here would be 1. And so I can plot it by putting a solid dot at 0, a solid dot at 1, and then connecting them to show that, okay, this interval 0 to 1 is plotted like that. Okay, and there's similar ways to plot all these other types of intervals. For instance, if I wanted to plot this ray 2 to infinity where I don't include 2, well then what I can do is I start at 2 and I draw a open circle to signify that, okay, I'm not including 2. This is 2. And then I can just extend off with an arrow this way, showing, I'm including every real number greater than 2, but not including 2. So we'll use this idea again, and we'll actually generalize that idea later when we look at functions and when we start drawing the graphs of functions in the xy plane. So the next thing I want to do is introduce a very important operation. And later we'll see it's actually a function, but that's the absolute value of a real number. So of a real number x, the absolute value is defined like this. It's defined actually as a piecewise function. So it's just going to be itself, so in other words, the absolute value of a real number will be itself if that number is greater than or equal to 0. But then if it's less than 0 or negative, I'm just going to say that the absolute value of a number is negative. So if it is negative, it will become positive. And this is also a great chance to introduce the piecewise notation that I'm sure you're familiar with. So for different parts of the domain of this function, or for different real numbers, it has a different definition. And we're going to see this time and time again. So again, lock this in your mind because it's really important. But notice that there's another way to define the absolute value of a number, and that's to take the square root of the number squared. And notice what happens here. If a number is positive and I square it and then square root it, I just get the number back. But if a number is negative, I square it, I get its positive square, and when I take the positive square root, I get its absolute value. All right, cool. So this is going to come up a lot, the absolute value, when solving equations and inequalities. So the thing to consider is that if I have a variable x, and I know that the absolute value of x is equal to some real number a, then one of two things can be the case. Either x is a, or minus x is equal to a, because I have to consider both parts of the definition. Either x can be a, or the negative of x can be a. And so that's what this equation means. One of these two things can be true to make the absolute value of x equal to a. All right, so now that we're getting our handle on the idea of sets and subsets specifically of the real line, let's just go ahead and reintroduce the idea of a function. And this is going to seem a little bit abstract at first, but it's really important to kind of get this idea in your head. So a function, which we'll denote for now just by a little f, sometimes we'll use different letters, but a function f from a set D to a set Y. And now these sets D and Y, we really want to think about them as subsets of the real line. So maybe an interval, maybe a union of two intervals, something like that. And so to give the definition, I'm just going to draw a picture. So we're going to start with our set D, and I'm just going to draw it as a, well, not really a circle, but a region. So here's D, and here's Y. And so what it does is it takes something in D, so let's say X is something in D, and what it's going to do is it's going to take it over into something in Y. And we'll call this something in Y, well, little y, like that. Okay, and this is the function. So the function is going to take everything in this set D and assign each thing in D to exactly one thing in Y. And now that's really important. That's, if you recall, that's like passing the vertical line test. So for every input of the function, we get exactly one output. And now the set D is called the domain of F, and this set Y is sometimes called the codomain. That word isn't as common as domain. That's what it's called. And so what we'll write is that this element Y in the codomain is a function, or is an output, of this input X in the domain. And when we use Y and X for these variables, we'll say that X is the independent variable for the function, and Y is the dependent variable because it depends on which X we choose for an input. But we're sort of free to independently choose X from the domain. But then once we pick X, we're sort of fixed into which output we get in Y. So that's the basic idea of functions. And just to kind of refresh your memory, we'll next give some examples of why functions are useful. So here are just a couple of examples, or actually specifically 3 examples, of different types of functions you may encounter. And so let's just identify what the independent and the dependent variables are. So in the first example, the position of a ball, which is given by the dependent variable s, is a function of the independent variable t. So for each time after the ball is kicked, I plug in t into my input and I get my output, which is the position of the ball. Same thing here. The dependent variable here is h, the height of a plant, and it depends on the independent variable d, which is the days after it was planted. So I have input, output. Same thing here. Dependent variable is pressure, P, and it depends on the independent variable, T, which is the temperature outside. So I plug in temperature outside, and that should give me a unique pressure in my car's tires. So there's a few examples, and I'm sure you can think of a lot of examples on your own. So I've talked about the domain and the codomain of a function. But in the calculus setting, and in a lot of settings, we're not explicitly given a domain and a codomain for a function. We're just given a function. We're given that y is some function of x. Maybe this is x squared, sine of x, e to the x. We're going to talk a lot about those examples later. But let's just say for now we have a function, and we have a dependent variable y, independent variable x. We're going to define two very important sets. And the first one is called the natural domain of f. And now notice this is a little bit different than the domain of f because I'm not actually going to specify what the domain is. I'm calling it the natural domain because it's exactly that. It's basically all of the real numbers x for which f of x is a real number. So let's actually write that in set builder notation. So we'll denote it by d of f. And what this is going to be is it's going to be all the real numbers such that f of x is a real number. So think about, for instance, if the function was 1 over x. Well, we can't divide by 0. So x would be excluded from the domain of 1 over x because 1 over 0 is not a real number. So we're just looking at the numbers, the real numbers, that we can naturally plug in to the function itself. The next concept is one that I'm sure you're familiar with, and that's the range of the function f. And so the range of f, which will denote r of f, is going to be the set of real numbers y for which what? Well, for which there is an x in the domain of f such that y is equal to f of x. So in other words, we're just looking at all of the real numbers that are outputted by the function. So you look at all possible inputs, and then you just see what happens when I plug in those inputs into my function. The collection of all possible outputs is the range of f. So here we have a bunch of different ways that we can combine functions. And again, I'm sure a lot of these are familiar to you, but I just want to put them here just as a reference and just to review. And notice that I've also included for each one of these ways to combine functions the definition and also what the domain is going to be. So for instance, if I have a function f, I can take a constant multiple of that function. So I can just multiply the function by that constant multiple, and that's just going to multiply all of the outputs by that, whatever that real number is, c. And that's not going to change the domain of f. And then we can add two functions. We'll see that the domain is just going to be the intersection of the two functions, the intersection of the domain of the two functions. Product of two functions is the same thing. You just take the product of the outputs, and the domain is, like I said, is the same. It's the intersection. Quotient is just like product, but we just need to add this extra restriction that the function that's in the denominator can never be 0. And then finally, the composition of functions is just going to be, well, you take the input of one function as the output of the other. And the domain is going to be basically wherever that makes sense. So here it is in set notation. You can look at that. But basically you just want, okay, I want the output of g to be in the domain of f. Otherwise it's not going to make sense to compose the functions. Another thing to notice about composition of functions is that it is in general not commutative, meaning that if I take f of g of x, that in general is not going to be the same thing as g of f of x. And that's going to be important later on. We're going to see some examples that really throw some curveballs into maybe the way you think about functions. So I just mentioned that function composition in general is not commutative. So for instance, let's suppose that f of x is equal to x squared and g of x is equal to square root of x. Okay, so let's think about what is f of g of x. Well, g just tells me to take the square root of the real number, and f tells me to square it. So what this is going to be is it's going to be the square root of x squared, which is x, with one condition. Notice that we first have to take the square root of the number. So that means the domain of this composition is going to be the same as the domain of g, meaning that the domain is not going to include any negative numbers. So the domain here is going to be x greater than or equal to 0. So this isn't really the function x where I can just plug anything in. It has a natural domain restriction. So what about g of f of x? Well, this is going to be the square root of x squared. And now what is this? This is something that we've already seen. This is absolute value of x. Now the domain of this function is going to be all real numbers, but actually the output or the range is what's interesting. We're not going to get any negative numbers. We're only going to get non-negative numbers. And so you see that these two functions are different. They have different natural domains, because I can't plug in a negative number here, and I can plug in a negative number here. So you see that the function composition is not the same. And this is an extremely important example, and I would really encourage you, if you're saying, what is going on right now, to really sit down and think about this example, because it illustrates how intricate functions can be. And when you start composing functions, how careful you need to be. Later on, we're going to see taking the square root of something squared, we're going to have to think about that as being the absolute value. And it's really interesting, and it's really worth spending some time thinking about. But we actually want to think about the case where this function composition is commutative. It does go both ways. And actually, in the special case where f of g of x equals g of f of x equals x, then we actually give these functions a special name. F and g are said to be inverses. And a lot of times we'll write the inverse of f in a special way. So the inverse of a function f is denoted f to the negative 1, like that, f inverse. And so another thing to note about the domain and range of inverse functions is this. Well, the domain of f is going to be the range of f inverse. That's really nice to know. And the range of f is going to be the domain of f inverse. And this really makes sense if you think about it, because to be invertible, if I start in the domain of f and I apply f, I end up in the range of f. Well, that better be in the domain of f inverse, because I need to be able to go back into the domain of f to sort of reverse the process. So again, function inverses is something that's going to play an important role in calculus, and so it's going to be really important to understand maybe the simplest example of two functions that do not have inverses, x squared and square root of x. So this leads us to a really natural question. And the question is this: does every function have an inverse? And the answer, of course, is no. And we've actually already seen an example of a function that does not have an inverse on its natural domain. And that function is x squared. And the reason it doesn't have an inverse is because, let's say I started with the number 2 and I squared it. When I went to go and square root or reverse the process, I have to make a choice. Do I mean 2 or do I mean minus 2? There are actually 2 square roots of 4. And so in a sense, you cannot put the toothpaste back in the tube for every function. So then the next natural question to ask is, when does a function have an inverse? And if you recall, to be a function, for every input, you had to have exactly one output. So if we want a chance to reverse the process, we better have for each output exactly one input. And so in other words, we want the function to be 1-to-1. So the answer is f, our function, has an inverse if it is 1-to-1. And so what does 1-to-1 mean? Well, it's exactly what I just said. For each output, there's exactly one input. And we can write this symbolically. So suppose that I had f of x equaling f of z. So I had two numbers x and z that gave me the same output. Well, then it better be the case, if this happens, that x is actually just equal to z. So it's not possible to have two different inputs giving me the same output. And you can see that when this is the case, the inverse function is actually well defined. It actually is itself a function. Because remember, my outputs become my inputs for an inverse function. And so if my output is here, I better have one input back in the domain of the original function. So now that we know when a function has an inverse, let's actually go back to our example of a function that does not have an inverse on its natural domain. And that's x squared. Has no inverse. And another way to say this that we'll say sometimes, so it doesn't have an inverse, in other words, it's not invertible. And specifically, it's not invertible on its natural domain. But what would happen if I just restricted the domain? So I know that 2 and negative 2 are going to give me the same output when I square them. But what if I only consider the non-negative numbers? So if I put a domain restriction, and by domain restriction, all I'm doing is just throwing out certain values that I don't want to consider in the domain. And in this case, those are the negative numbers. So I'm going to restrict my function f to the set 0 to infinity, and I'll include 0. And so on this restriction, the function x squared is 1 to 1. Thus, it's invertible. But it's only invertible when I consider this function x squared on this domain restriction, the ray from 0 to infinity. And of course, in this case, the inverse is exactly what we expect it to be, just square root of x. So this brings up a very subtle point that we'll see again. We have a function that is not 1 to 1, so it's not invertible, on its natural domain. However, if we restrict the domain to a smaller set where the function is 1 to 1, then it is invertible, and we can find an inverse. We're going to see this again when we talk about the trigonometric functions. In general, trigonometric functions will not be 1 to 1. They're not going to have inverses, so we're going to have to narrow in on a small interval for which they are 1 to 1, and then we'll be able to define an inverse. So it's a little tricky, but again, if you can understand this example of x squared and square root of x and realize that they are only inverses when I restrict the domain, then you're going to be taking a lot of huge steps towards understanding kind of the basic ideas behind functions that we need to understand moving forward. Okay, so let's get our hands dirty. Let's solve this equation. Now notice there's an absolute value here. So we got to consider actually two cases. So the first case is that what's inside the absolute value is positive. So in other words, x minus 2 is equal to 4. The other case is if we have a negative inside the absolute value, because that's going to be fine too. And in that case, we'll have negative x minus 2 is equal to 4. Okay, and so we have this very important word, or. So either one of these equations could be true to make the initial equation true. So if we go through and solve, we'll get x is equal to 6. So I'm just going to add 2 over there. And over here, let's multiply by negative 1. So I'll have x minus 2 is equal to negative 4. Or in other words, x is equal to negative 2. So we actually have two solutions. X is equal to 6 is a solution, which you can verify, or x is equal to negative 2. So there are two solutions to this equation. Okay, so here I have an inequality that I'm trying to solve with an absolute value. And unfortunately, with these inequalities, you just have to think when you solve them. There's really not a great way. I mean, there's some methods that you can sort of memorize, but the best way to solve them is just to think about it. Now, the first thing I'm going to do is isolate the inequality. So I'm going to subtract 1 from both sides. So I have absolute value of x minus 2 is less than 3. Here's where I have to think. How can this be true? Well, x minus 2 could just be less than 3, but at some point I'm going to have a problem. And that's when if x minus 2 gets so small that it's actually less than negative 3. Because if x minus 2 is, say, negative 4, when I take the absolute value, that's not going to be less than 3. So I really have two things that must be true for this inequality to hold. The first one is that x minus 2 must be less than 3. But I also need, so I'm putting and here to signify that this also needs to be true. X minus 2 must be greater than negative 3. And again, that's because what's inside the absolute value, when I take the absolute value, must be less than 3. And if x minus 2 is less than negative 3, when I take the absolute value, I'm going to get something bigger than 3. Okay, so I need to solve both of these inequalities. For the first one, I get x is less than 1. No, not 1. I'm going to add 2, so x is going to be less than 5. There we go. And then here, I'm going to have x is bigger than negative 1. So I get two intervals. I have x less than 5, so that's negative infinity to 5. And then I have x bigger than negative 1. So that's going to be negative 1 to infinity. And the key word is and. I needed two things to be true. And I got two distinct sets. So the and tells me I actually need to intersect them. So the solution is going to be the intersection of these two rays. Negative infinity to 5, intersect negative 1 to infinity. And what do I get? I want all the numbers less than 5, bigger than negative 1. Well, that's just the interval negative 1 to 5. So this is going to be my solution set. So this is really similar to the last problem. We're solving an inequality, but notice this time the only difference is that we have an inclusive inequality. So I'm actually going to be including this boundary point of 5. So x squared plus 1 actually can be equal to 5. And then of course it can be greater than 5 as well. So again, I'm going to start by subtracting 1. So I have x squared needs to be greater than or equal to 4. And then I'm going to take the square root of both sides. And this is really important because we're going to see this time and time again during this course, but it's important to recognize this now. When I take the square root of x squared, I don't get x. I get absolute value of x. And when I take the square root of 4, maybe you're in the habit of saying, oh, that's plus or minus 2. No, the square root of 4 is 2. But when I take the square root of a variable squared, I need to consider the fact that the variable could be negative as well as positive. So actually this is equivalent to just saying absolute value of x is greater than or equal to 2. Now if I want absolute value of x to be greater than or equal to 2, actually two things can happen. Sort of like in the last example, I needed two things to happen to be less than 3. Here, one of two things could happen for absolute value of x to be greater than or equal to 2. The first one is that x could be greater than or equal to 2. But there's also something else that can happen. So I have an or here. I could also have x being so negative that when I take the absolute value, I end up with something greater than or equal to 2. So in other words, x could be less than or equal to negative 2. Because then when I take the absolute value, I will be greater than or equal to 2. And again, the key word here is going to be or. So I get two solution sets here for my two cases to consider. One of them is 2 to infinity, and the other one is negative infinity to 2. And the key word here is or. So with and, I took an intersection of the two sets that I found. With or, I'm actually going to take the union. That's negative 2. So the solution set is going to be negative infinity to negative 2 union 2 to infinity. And you see that any number in this set, when I take the absolute value, will be greater than or equal to 2. So here's my solution set. Okay, so we want to find the domain and the range for this function here. So I'll tell you that the domain is typically easier to find and also more useful to find. The range is really interesting to find, but a lot of times in practice, it's not as necessary. But here, the domain, recall that we want the real numbers for which we get a meaningful output, or in other words, the output is a real number. And here, the only problem we have is if we had a negative under the square root. So for the domain, we want to require that x plus 2 be bigger than or equal to 0, because I can only take the square root of a number that is bigger than or equal to 0. But that means that x has to be greater than or equal to negative 2. So then the domain of this function is just negative 2 to infinity, including negative 2. Okay, so the range is a little bit trickier, and it requires maybe some clever observations. So the first one is that notice that f of x is always greater than or equal to 0. So we might be suspicious that the range of f be 0 to infinity. And now you say, okay, great, well, we're done. Well, no, we're not, because this is really just a guess. I'm just assuming that, well, for every number between 0 and infinity, I can find a number x such that the square root of x plus 2 is that number. To actually prove that the range is this set, I need to take a y in this set. So if I take a y here, and I set it equal to square root of x plus 2, so this y is just going to be a number between 0 and infinity. Well, if I square both sides, I get y squared is equal to x plus 2, or in other words, x is equal to y squared minus 2. Okay, so why did I do this? Because what this allows me to do is see, okay, for every y between 0 and infinity, I can actually find an input. What is the input? Y squared minus 2. So that when I plug that input in here, I'm actually going to output y. And so I can actually conclude that the range of this function is 0 to infinity, including 0. And here, of course, was the domain. All right, so let's start with the domain. And actually here the domain is really easy. So when you're looking for the domain of a function, you're looking for things like square roots and denominators. So you can't have negatives under square roots, and you can't have zeros in denominators. Well, there's no square roots or denominators here. So the domain is actually all real numbers. There's no problem. We can plug in any number, any real number, in for x, and we'll get a real number as an output. Okay, so let's look at the range. So the range, again, we're going to have to use some clever observations. And first of all, notice that x minus 3 squared is greater than or equal to 0. Okay? And if I subtract 2, which is, of course, just f of x, so x minus 3 squared minus 2, well, I've just subtracted 2 from both sides of this inequality. So f of x appears to always be greater than or equal to negative 2. So we might guess that the range is going to be negative 2 to infinity, including negative 2. But we actually have to justify that. So if I pick a y in the range here, between negative 2 and infinity, I need to actually show that there is an input that gives me that output. Okay, so I'm picking a number y between -2 and infinity. And so I want y to be x minus 3 squared minus 2. So I can add 2. And then we have x minus 3 squared. I'm going to take the square root of both sides. So I have square root of y plus 2 equals, well, really I'm going to get absolute value of x minus 3, but I'm just looking for 1x. So let's just take the positive square root, so x minus 3. But then look, as long as y is greater than or equal to -2, this will be a real number, and I can take x to be square root of y plus 2 plus 3. So this input that I choose, given any number y in here, will give me an output of that y when I plug it back into the function. Therefore, the range will be this set. And we've already found the domain. Okay, so let's start with the domain. So notice that the only problem here is if the denominator is 0. So we're going to require that x squared minus x not be equal to 0. And so the way I'm going to solve this, now this is sort of strange, but I can treat this just like inequality. But I'm just saying, well, I just don't want it to be equal to 0. So I can factor this as x times x minus 1 not being equal to 0. So now for this to not be 0, both of these can't be 0. So we better have that x is not 0, and then of course here x can't be 1. So we have again, and both of these things need to be true. X cannot be 1. So the domain, well, we can just write it as x not equal to 0 and x not equal to 1, but just for fun, let's write it in interval notation. So we'll have negative infinity all the way up to 0, not including 0, union 0 to 1, of course not including 0 or 1, and then 1 off to infinity, not including 1. So there's the domain. So the range here is a little tricky, and you just have to kind of go with your gut. So let's suppose that we're looking for the range here. And I want to notice right away something that's true, that f of x is never equal to 0. And why is that? Well, the only way that f of x is going to be 0 is if the numerator is 0. But the only way the numerator is 0 is if x is 0. But x is not in the domain of the function, so f of x can never be 0. So I'm just going to make a guess. Now, it's a very educated guess. And the educated guess is going to come in what we do next. And really, I'm going to solve this problem by working backwards. But I'm going to guess that the range of this function is actually negative infinity to 0, and then 0 to infinity. So basically every real number except 0. So let's say that we had a number y in this range. So I need to show actually that I can find an input given any y here. I can find an input that when I plug that input in, I get y. So I would like y to be x over x squared minus x. So let me just switch some things around. And so we'll have y times x squared minus x. And here what I'm doing is I'm just going to cross multiply equals x. And then, so I'm trying to solve for x here. So this is y times x squared minus yx is equal to x. And let me subtract x over. So I have y x squared minus yx minus x is equal to 0. Okay. And let's see. We have, this is going to just be yx squared. And then here we'll have y plus 1 times x is equal to 0. Okay, and then we'll go up here. So this is definitely some algebra, and I'll go ahead and, I wrote this before, but I'll say it now. The hardest part here is algebra. And so, okay, I want to factor this. I want to factor the x out. So I have an x times, this will be y times x. And then what's left over here is minus y plus 1, so just minus y minus 1. And so either x is 0, but remember that we're actually excluding x equaling 0 because it's not in the domain. So that means it must be the case that yx minus y minus 1 equals 0. Okay, so let's just solve for x. So this is going to be yx equals y plus 1, and then I can divide by y. So that x is equal to y plus 1 over y. And notice that y is not 0. Y is a number other than 0. So as long as y is not 0, I actually get a meaningful input here. And that input is going to give me y when I plug it back into the function. Okay, so that proves my guess. And really what I should say is that my guess came from first solving essentially for an inverse of the function and seeing what inputs I need to give me specific outputs. And of course, here's the domain. So like I said, finding the range is a little bit difficult. It's a little bit more theoretical. It involves a little bit of proof technique that we're not going to get into a lot in this class, but that's how you do it. And then the domain, again, we're just looking for no negatives under square roots, and then of course no zeros in the denominator of fractions. Okay, so we want to determine whether this function is one-to-one, and if it is, find the inverse. If it's not one-to-one, then we'll find a domain restriction for which the function is one-to-one, and then we'll find the inverse of that function. So with this first function, okay, so the first thing to notice is, well, the domain is all real numbers. Okay, so is it one-to-one on its natural domain? Well, to do that, we want to set f of x equal to f of z, not assuming that x and z are the same, and actually show that x has to equal z. So f of x is 3x plus 5, and then f of z is 3z plus 5. And if you look, we can subtract 5 from both sides, so 3x has to equal 3z. And if we divide both sides by 3, we have x is equal to z, which is what we want to show. Therefore, f is one-to-one. Okay, so it has an inverse. And how do we find the inverse? Well, this is something that you may have seen before. What we're going to do to find the inverse is we're going to say, okay, the function y is my dependent variable, or it's my output. And all we want to do is switch the input and the output. So we have x is now going to be my input of my inverse, and my output is going to be y. Okay, and then just solve for y in terms of x for our new function. So I subtract 5. So we'll have 3y minus 3y equals x minus 5. And then if I divide by 3, I have y is equal to x minus 5, all divided by 3. Okay, so this is the inverse function. So f inverse of x is just x minus 5 divided by 3. And notice that if I compose these two functions, if I take f of f inverse, I get x, and if I take f inverse of f, I get exactly x. So right off the bat here, we see that this function is not one-to-one. And that's because f of 2 is equal to f of 4, which is equal to negative 1. Okay, so because 2 is not equal to 4, but 2 and 4 give me the same output, this function is not one-to-one. So what we need to do is restrict to a domain for which f is one-to-one. And how do we do that? Well, notice that x squared, if we require x to be greater than or equal to 0, is one-to-one. So what we're going to do is we're going to require here x minus 3 squared, x minus 3 be greater than or equal to 0. Or in other words, x greater than or equal to 3. So we're going to so in that case, x minus 3 squared is one-to-one. Subtracting 2 isn't going to change anything. So the domain restriction that we're going to use is 3 to infinity. We could also use negative infinity to 3. And actually, that would still be correct. That would be like the negative. When we take the square root, it would be like taking the negative square root. This is going to be like taking the positive square root. But this is the domain restriction that we're going to use. And so in this domain restriction, we can invert the function. And so remember that we do that by saying, okay, well, my output y is given by x minus 3 squared minus 2, and I'm just going to switch the input and the output and solve for the new output. So I'm going to add 2, so I'll have y minus 3 squared is equal to x plus 2. Then I'm going to take a square root, so that's going to be y minus 3 is equal to square root of x plus 2. And now here's where I'm saying I'm taking the positive square root by choosing this domain restriction. So here when I take the square root, I'm really going to be taking the positive square root. And then I can add 3. So y is going to be x plus 2 plus 3. So in other words, my inverse function here is going to be square root of x plus 2 plus 3. And you can verify that if I compose f with f inverse, I'm going to get x, and if I compose f inverse with f, I'm also going to get x. Okay, so the first thing to notice is that this function is one-to-one. And why is that the case? Well, if I set f of x equal to f of z, if f is one-to-one, it better be the case that x is equal to z. So this is 1 over x plus 2. This is 1 over z plus 2. And if I cross multiply here, I'll get z plus 2 equals x plus 2. Subtracting 2 from both sides, I see that x is equal to z. So f is 1 to 1. So now it's just a matter of finding the inverse. And we do that by switching the input and the output. So for an output y, for our function with input x, 1 over x plus 2, let's just see what happens if I want my input to be my output. Then I'll have y plus 2. And so notice that negative 2 is not in the domain of this function. Okay. So let's see. We'll have, let me cross multiply again. We'll have x times y plus 2 is equal to 1. Then we will, let's see, we can divide by x here. And now, so I said that negative 2 was not in the domain of this function. Also notice that 0 is not in the range of this function. And so the only way I'm going to be able to get 0 is if the numerator is 0, but the numerator is never equal to 0. So that's why it's actually okay that I'm dividing by x here. Because remember, x is going to be the input of my inverse function, meaning it's an output for my function. So 0 is not in the range of my function, so it's not in the domain of my inverse function. And then I can just subtract 2. So then my inverse function is just 1 over x minus 2. And that's the inverse function. And again, you can verify f of f inverse will give me x, and f inverse of f will also give me x.